Welcome and good afternoon. Thank you very much for taking the time out of your schedules to join us today. I'm Tony Henderson, Assistant Director of the Development and Alumni Relations Office, and I'm delighted to be joined today by Professor Sabine Hauert, who will be telling us about swarm robotics and how it can benefit people. So without further ado, I'd like to open today's event. We're delighted to have Professor Sabine Hauert here with us. Sabine is Associate Professor of Swarm Engineering at the University of Bristol. Her research focuses on making swarms for people and across scales, from nanorobotics for cancer treatment to larger robots for environmental monitoring or logistics. Sabine is also President and co-founder of RoboHub.org and Executive Trustee of AIHub.org, two non-profits dedicated to connecting robotics and AI communities to the public. Sabine, over to you.
Thank you so much for the introduction. It's a real pleasure to be here today. Today, I wanted to bring you on a journey looking at how we can design swarms for people and across scale, from nanoparticles for cancer treatment to larger robots that could be used for things like environmental monitoring or logistics. And really, as a swarm engineer, my source of inspiration is these flocks of birds. If you look at them, they can do beautiful, complex dances in the sky, and there's many features that are useful for real-world applications. For example, if you keep adding birds to the flock will continue to fly, and so they can scale to huge numbers. If a bird falls to the ground, the whole flock doesn't crash to the ground, so they're robust to individual failures, and together they can do more than the sum of their parts. For example, they might be better at avoiding predators as a flock than any of those individual birds. And what's quite remarkable is that these beautiful dances that emerge as a result of every bird in this flock reacting to their local environment. There's no leader bird, there's no grand plan telling every bird what to do. It's every bird simply reacting to their local environment that gives rise to these beautiful patterns in the sky. And this is what we call self-organization. And we see examples of self-organization everywhere in nature, whether it's these flocks of birds or ants as they create a trail to your picnic table, or bees as they make decisions about their next nest site, or indeed our ability to grow fully functioning human shapes just from a couple cells. Now, the challenge for swarm engineering is that very often you know what group behavior you want to achieve. You might want collective motion like the birds, or trail formation like the ants, or decision making, or you might want to grow functional shapes, but you need to crack this puzzle about how do you design those individual agents and their local interactions, because that is what you need to figure out to be able to get your desired collective behavior. So typically in my team, we do that using two techniques. One is to use bioinspiration. So we're very lucky that biologists have studied a number of self-organized systems and have rules for them that we can then adapt to engineered systems. We can also take inspiration from chemistry, from physics, anything that deals with lots of agents that interact. And when cases when we don't have bioinspiration to work from, in that case, we typically need to explore those local interactions, those rules. And so how might we do that? We might do that by guessing. So you could imagine the student in front of a computer trying to guess the rules and observing what emerges. You could do that with lots of people guessing, which is a form of crowdsourcing, or you could do that, and this is what we do increasingly using machine learning. So an automatic way of exploring those local designs that give rise to desired collective behaviors. Now, the fun thing is that when you do have the rules, for example, in the case of bioinspiration, you can go ahead and put them on flying robots here, for example, and throw them in the air. I'm behind the camera here. This is 10 flying robots that we designed over in Switzerland. And here you can see their GPS trajectories, and it starts very messy, but over time you get these circles, and that's indeed what we predicted in simulation. You can put these rules on the robots, throw them in the air, and they create these flocking-like patterns. And if you're curious here, there's just a small set of rules used. One is that these robots are attracted to their neighbors. That's what allows them to stay as a group. They're also repulsed from their neighbors, because if they were only attracted, they would all crash. So the repulsion makes sure that they can keep a distance. And they also try to align to their neighbors. And those 3 rules gives you flocking. And then we add a rule so they're attracted to 0, 0, which is our migration rule. And so that generates just those 4 forces, these dances in the sky. And this is something that's been used in other areas inspired from the birds, that we can basically put on the flying robots. Now, this was fun when I was working in this area, but it was 10 robots. And in my mind, swarms needed to work in much larger numbers. And so I got quite excited about the area of nanomedicine. I spent 3 years over at MIT in the laboratory of Sangeeta Bhatia. And in her laboratory, she was exploring how nanoparticles, which are nanometer sized, so they're really small, can, because of their size, go through blood vessels in the body and then leak out into certain types of tumors. And those properties made them interesting vehicles for the delivery of drugs or diagnostics within these tumor tissues. And what got me excited was the fact that in one of these injections, you would have 10 to the power 13 nanoparticles. So that was a proper swarm in my mind. That was a good number that we could start to think about, how do all these particles interact in these complex tumor environments? And the particles that the laboratory could make would have different sizes, they would have different shapes. This might be a little iron oxide nanoworm. They had different charges. You could also make them of different materials, and some of them were energy receptive, so you could use light or magnetic fields to activate them. You could decorate them with molecules that allowed them to bind to certain receptors overexpressed on some cancer cells, so they could recognize the cancer cells. And you could load them with drugs that they could release in a more or less controlled fashion. So you have many knobs that you could turn on the design of these particles. You could change their size, their shape, their cargo, their material, and their coatings. And depending on how you turn those knobs, that changes what the 10 to the power 13 particles do within that tumor environment. And so to start wrapping my head around this question, I started wondering, well, what if we just turn 2 knobs in a very simple model to start to see if this was even a useful question to ask? And the 2 knobs that I turned were the size of the particle. And you can imagine smaller particles go faster than bigger particles as they move through tumor tissue. And the other knob that we turned was how sticky these particles were to cancer cells. So here what you're seeing is a little scenario where we have a vessel, particles arrive through the vessels, leak out, and here we have a tumor tissue. And our goal is to kill up to 20 cells deep within this tumor tissue. And our particles can stick to the cells, at which point they get eaten up and can accumulate at levels that would kill the cells. And so the question is, how do you turn these 2 knobs on the size and on the stickiness of the particle so that the collective behavior of those particles allows them to kill all the cancer cells? And so this is something that we can do mathematical modeling for. And here what you're looking at is lots of different nanoparticle combinations based on their speed and based on their stickiness. Our goal is to kill 20 cells deep, which is the dark red. Some of them can kill 20 cells, but most of them can't. And something that was really interesting for bioengineers is that they had a nanoparticle that was really sticky, and that's worked great in a dish. So if you had this sticky particle, you'd put it in your dish of cancer cells, they would stick to all the cancer cells and kill them. And that sounded like a great strategy. But what happened when you put this in these tissue models, when you think of space, when you think of the numbers, is that these particles leak out of the vessel and all stick to the first cells they encounter and never go those 20 cells deep. So that's an example where the individual design made sense, but the collective behavior that results from that individual design does not work well. And just turning those 2 knobs basically gives you the full spectrum of how these particles might distribute in a tumor tissue. Since then, we've built more sophisticated models. So now we can see these particles sticking on the surface of these cancer cells. So we have a better resolution in space. And we've also built little microfluidic devices with a little tumor on a chip, which is basically a little tissue-like environment with microparticles here in red, but we can also put cells in there. And in green and blue, you're looking at real nanoparticles as they move through our little tumor tissue on a chip. so that we can start to validate some of the elements from the computational models. And if you're wondering where are the robots, don't worry, we'll be tying back to the robots in a little bit. The other thing that we've been looking at is, given these first models that we've built, can we build a framework that allows us, given a tumor specific properties that might be specific to a patient, for example, could we grow a virtual tumor, a sort of digital twin of that patient's tumor that captures the important elements that we cared about? And can we use the growth of this tumor tissue in silico to basically carve out lots of little tumor tissues, a little bit similar to the one you saw before, as basically tests or experiments in the computational world that we can then use to automatically design nanoparticles. So this is what we've just published this year. It's a new framework that allows us to use machine learning, a form of reinforcement learning actually, to automatically turn those knobs, tweak the design of the nanoparticle so that it can optimally treat all these virtual tumor tissues that we're giving it. And then the idea is that would give us useful guidelines for bioengineers who would then need to go ahead and make that nanoparticle for the specific patient scenario. So that's part of a big European project that we're currently wrapping up right now. And if you can model things that enter the bloodstream and then go through the bloodstream and end up in tumor tissue and accumulate in cancer cells, you can also model the reverse. So this is work with Katrina Kirian's lab, and this is funded by CRUK, where basically we model, instead of modeling nanoparticles that go to tumors, we model markers that leave brain tumors in this case. And we model how these markers leave the brain tumor, enter the bloodstream, and how we could take a liquid biopsy, a blood sample, to detect those biomarkers for brain tumors. And at what levels can we detect them? Can we tie the detection limits to the size of the tumor that we're able to capture? So these modeling of these complex dynamics for very simple entities is something that's quite exciting for the biomedical crowd in the context of cancer research. Now, coming from the swarm engineering perspective, I was still excited about this idea of making swarming nanomedicine. And so I went out and designed a game called Nanodoc that allowed us to crowdsource the design of these nanoparticles. And in this Nanodoc game, we had tumor cells, we had healthy cells. You might wonder why we had healthy cells. Well, the solution to every treatment would be to dump loads of drug in the system if you don't have the healthy cells. But the healthy cells make sure that you're a little bit more specific and not toxic to those healthy cells. We could change the dosage, and when we inject those nanoparticles, we could combine nanoparticles. We could change the size of the nanoparticle. We could have cancer cells that had receptors on their surface and nanoparticles that had a coating that would stick to those cancer cells. We could load the nanoparticle with a drug, for example, or something else. And we could create a smart material where if something activates the nanoparticle, it releases something in its environment. And then we can do self-assembly or disassembly, which, you know, my flying robots, we can make them go left or right. And we can't do that with nanoparticles. They just diffuse, they move randomly. But through self-assembly and disassembly, we can make them bigger or smaller, and that allows us to speed them up or slow them down. So actually, if you're a roboticist, you start thinking, well, wait a minute, these particles can sense their environment. They can act on their environment by releasing something. That thing they release can activate another nanoparticle. So now we have a form of communication. And although we can't easily steer them, we can make them speed up or slow down, which gives us a form of motion control. So we had around 120,000 simulations from the crowd. This is them designing a particle that was too sticky, or a particle here that's a bit less sticky, that's able to better treat this virtual tumor tissue. This is an example of a more sophisticated treatment that had two particles. So they would leave this vessel, and they have interesting features and dynamics. Here you have a particle that basically moves through the system and releases something to communicate to the second particle. So you sort of have interesting synergies between these particle systems. And so sometimes we also use this game to explore some of the swarm behaviors we knew. So this, for example, is inspired from how ants create trails to your picnic table. And usually they do that by depositing pheromones, little chemicals in the environment. And here we do that in a simplified way because our particles are simpler than ants, yet we have the similar rules as a starting point to be able to design this. And you can see using our simple rules, and I'll tell you about the rules in a minute, you can create these little trails between this vessel and then something you might be interested in finding within that tumor tissue. Now, it's great to be able to give guidelines about how to design nanoparticles. And some of this is actually quite near term in terms of how it could be used in the clinic. But some of the more sophisticated things we're proposing, where particles cooperate more explicitly, are further down the line, and they're hard to engineer. You would need a chemist, an expert in nanoparticle design, to make that system work. It would take maybe a PhD or depending on the sophistication of the particle, or longer, to make that specific particle that we've optimized in simulation. And so we set out to create a new playground for nano and microsystems to explore how they could cooperate in more sophisticated ways. And it could be nanoparticles, it could be bacteria, it could be mammalian cells, it could be protocells, microparticles. So anything that's small, basically, but that works in large numbers. How can we give them these capabilities that we're interested in without having to do all the chemistry behind there, or the biology behind there to start out with, at least to wrap our head around what we can achieve. And so with this in mind, we created a new platform called the DOME for Dynamic Optical Microenvironment. And what the DOME is essentially a projector that projects thousands of pixels independently. And each one of these pixels can be basically zoomed in to be the size of a cell. So we can make really tiny pixels where each pixel could interact with a cell, for example. And then below that substrate, we've got a camera that can see what's happening. So imagine you have your sample, which is a swarm of some type. You can see what's happening based on the projection. And then you take that image and you change the projection. So we have closed loop control using light of these nano or these micro collectives. And the fun thing is that Anna designed this platform to be all open hardware. So you can 3D print it, buy off-the-shelf components, assemble it. She has a little YouTube video of her assembling it. And it costs around 700 pounds or so to make yourself. And this provides us with a playground in which we can give our microagents augmented capabilities. So what you're seeing here on the left, or actually in this slide, are three building blocks of swarming. One is communication. So how do agents communicate? The second one is called stigmergy. It's how can they communicate through the environment, a little bit like depositing those pheromones for the ants. And the third one is motion control. And what you're seeing here is real volvox. They're little algae, living algae. And in blue, you see the dome projecting little communication halos around them. So we're augmenting the capabilities of these real volvox with a form of communication. So when they turn blue, that means they're communicating within a certain range. And you can see these blue messages propagate within the collective of volvox. And we can play around with the communication range to sort of wrap our head what would make for interesting communication dynamics in this collective. Here you're looking at stigmergy, so they're depositing light trails in the environment. And you can see sometimes this one, for example, is going to stop in the light trail because it turns out that light on volvox tends to stop them in their tracks. So you now get this interaction between the light trails created and the volvox movement. And then here what you're looking at is us controlling their motion by stopping them using light. And actually they stop when you blink light on them. And they all behave in slightly different ways. If you keep the light on, they'll get used to it and then just carry on. And so something that we've been doing is using learning, a form of Q-learning, to be able to automatically figure out what the optimal blinking pattern is so that we can adapt to every individual volvox because they're all slightly different. And this ability to control collective has got us excited about how we might use this in the biomedical field. So for example, we've started asking the question of, well, where do we see collectives of cells where we might want to control their motion? And indeed, skin is an interesting area we might look. And so for the past year, we've been working with a team of biologists and bioethicists and engineers to understand where we can use, if we could take the dome and make it a wearable or something that we could put a wound in, and whether we could use light to help us basically guide the cells to close the wound in a more efficient way, in a closed loop manner. And maybe you could even include something interesting in there, like learning to adapt to that specific wound on the go. So that's something that we've just started to scratch the surface of, but where there is potential to control collectives towards more biomedical applications. So that was the nano and the micro world, which tends to work in huge numbers. And all of those rules are bio-inspired. And that's also made us change the way we think about robots. So if you think of robots planting seeds in a farm, you might imagine robots that zigzag through that farm and plant seeds sequentially, right? And actually, if you think of it in the way we think of the nano and the micro world, maybe instead you would design 100,000 robot seeds that buzz through the farm and go and plant themselves, maybe with little water bubbles that have just the right amount of nutrients to sustain that seed's growth. So a very different way of thinking about how you deploy a swarm of seeds in this case. And many of the rules we found at the nanoscale would work on very simple robots. So I actually have on my desk, I have a bunch of these little, they're called kilobots, and they're little coin-sized robots. They have 2 vibrating motors that allows them to move around. They're very noisy, not just the noise, but in how precise they are in their motion. They can communicate within 10 centimeters. They have an LED, so we know what state they're in. And they also have a light sensor, so they can sense the light. And here what you're looking at is the trail algorithm I showed you in the nanoparticle simulator. We release the robots, they do random motion, they find the second robot. This robot can communicate very nearby, and that stops nearby robots who then start to communicate. And really quickly, you grow these trails from the area of input to an area you're interested in. And because it's all self-organized, you can avoid obstacles, you can find the nearest object. So you get many elements for free. And the interesting thing for me is this is all random motion and very simple local interactions. So we can create this using very cheap robots. We don't have to calibrate. It actually scales to quite large numbers of robots. Here what you're seeing is 400 robots. These robots are, again, random motion, very simple local interactions. They're using an algorithm inspired from honeybees making decisions. And here you can see blue and red now, and they're trying to converge to blue. So make a decision blue, which is the right decision to make. And here they are all blue. Some of them are green. Those are noise robots that are trying to mess with the swarm, but they don't manage. And so this is an example, again, of random motion, very simple local interactions. And yet you can get these collective decisions emerge in a very systematic way. And here what we're looking at is robots, the exact same robots pretending to be cells. And what we were hoping to see is if we can grow shapes, and a little bit like we grow shapes through embryogenesis. And this is work actually with James Sharp, who is an expert in embryogenesis in biology. And what he knew was that certain types of cells do this reaction. So they have 2 chemicals called morphogens, and this chemical U activates V and itself, and this chemical V inhibits itself and U. This is what we call a reaction network. It was described by Alan Turing, and it's what generates spots and stripes and skin in animals, etc. And then each one of our robots basically runs this reaction. So they're storing in their memory 2 morphogen values. They run this reaction, and then they send these concentrations of morphogens to their neighbors through communication. That's what we call diffusion. And then what we have here that emerges, just like you'd expect in biology, is spots. So spots emerge in areas with high morphogen concentrations. And if you change the parameters, you could get stripes, for example. So with 300 of our robots, we noticed that if we ran this reaction network, we could define patterns. And these patterns are these spots. And then unlike biology, we cannot replicate or kill robots. And so what happens instead is we remove robots from areas where there's low concentrations of morphogens to areas where there's high concentrations of morphogens. And so that basically allows us to grow little limb-like structures, little protrusions from the areas where the spots are. Just to give you a sense of what this looks like. Here you can see these shapes grow, and they always create similar shapes, even though there's no grand plan of the shape. But you can see like these protrusions emerge. And because it's self-organized, we can chop off some of these protrusions, some of these legs, and they regrow. It looks quite organic. You can kind of imagine this as a cellular system. So we can chop them off and they'll regrow, or if we chop it off too much, it'll just reallocate robots. And you can split it and it will self-heal. It's fun as well because as that happens, the spots, those Alan Turing spots keep moving around. So we're able to essentially continuously adapt to the shape that the robot is in. And we can also do this more controllable as an engineer. We don't want to just have any shape that emerges. And so we also discovered if we put gradients on the shape, we can guide the growth of the limbs. So we can make short and stubby limbs or longer elongated limbs. And those are things that we can tune using a couple of parameters. And then finally, in the shape formation, we've also been thinking about how do we create shapes without having that full shape full of robots, because that takes a lot of robots. And so here instead, what we're trying to do is grow shapes using salient features. So here you can see a line that's projected, a circle that's projected, and an arrow. And we don't create the shapes by having them chalk blocked full, but we create the shapes by basically being able to self-organize on the edges of those patterns so that we can use a little less robot material. And again, it's self-organized. So if you go a little bit further to a simulation with 1,000 robots, this is exactly the same algorithm as you saw before, but because the shape moves, you create animations, and that's all given to us for free through self-organization. Okay, so now you might be wondering, well, if we create lots of robots, what will these look like? Will they actually be, electronic pieces, which wouldn't be very sustainable? And so something we've been wondering about is how could we create robots that might be single-time use, but biodegradable in their environment? And we wondered whether something like little hopping robots could help us cover an area and be used for sensing. So here we're just simulating a bunch of robots jumping over an area, and they work because there's enough of them that probabilistically you cover the whole environment. And if you have the right number of jumps with the right length, you can get really good coverage as opposed to kind of piling all those robots up in one spot. And you can also see what these robots might look like. Well, they look very different from the electronic robots I showed you before. These are robots that are preloaded. You can imagine kind of a robot tree, like building them one after the other and then popping out. This is the robot changing color, based on the temperature it senses. So the sensors are painted on them. And this is the robot jumping, basically powered by water, because those little latches that you saw before dissolve in water. And so if it rained on this robot, you would then power the jumping. And so right now we're working on figuring out what material we can replace just the band with to have something that's more biodegradable, whether it's a kind of wood or another biodegradable composite. So I mentioned at the start that bioinspiration is one of the main ways in which we've been exploring these swarm behaviors. And you've seen many examples now of bioinspiration through the robots and the nanosystems that we've designed. But there's also a very important one, which is exploration, and in particular, machine learning. So here what you're looking at is a swarm of robots about this big. And these robots are learning how to swarm on the go. Their mission is to push a frisbee from the center of the arena to one side of the arena. And these robots they're called the Teraflop Swarm. Why is that? Every robot has a GPU on board. And this GPU allows it to basically learn how to swarm on the go without any external computation. And if I play this again, imagine this takes 15 minutes in real time. It starts very messy, but over time, see, still not very good at it. Over time, they get better at pushing this frisbee to one side of the arena. For those who are interested, it's a form of reinforcement learning called artificial evolution. And I'd be happy to answer a question about what artificial evolution is. But basically all it is we try random programs, but this is done in simulation on the GPU of the robots. And they're going to try that program for themselves in simulation. And then if it's good, then that program gets improved over time. And if it's not a good program, then it gets thrown away. And so you do this generation after generation after generation until good programs emerge on the robot that give rise to these collective behaviors. So thanks to the computation that we now have and the machine learning tools, we can also figure out how to swarm on the go in relatively short amounts of time in these more simple scenarios. And the thing that we care about is that at the end of the day, we can peer into the brain of that robot and understand what it's doing. So the things that we evolve are called behavior trees, and it's taken from the gaming industry. And the reason we like behavior trees as opposed to more black box methods is because we can read the behavior. So we know through this tree what the robot is doing at different points in time, and we can color code it, and that gives us some intuition about the individual rules that gave rise to the collective frisbee pushing that you just saw before. And I think that's going to be important for human users to understand what it is the robots are doing. So I hope I've convinced you that we're at a stage in swarm robotics where we can create simple robots in huge numbers, more sophisticated robots. We can create algorithms in different ways. And so I think it's now time for us to get these swarms out of the lab and to people. And so the first step for us was to understand what people wanted with this technology. So we built an escape room before COVID, where we could lock people in for 30 to 40 minutes. They would go and do puzzles about swarming to get out of that escape room, and they would learn about swarm robotics on the way. And we asked them about what types of technologies they'd like to see happen, and what the risks and benefits for society were. And there's a number that we had already been thinking of in the swarm community, like construction, inspection, nuclear decommissioning, pollination, farming, search and rescue. And there's a number that I hadn't thought about, like massages, that didn't cross my mind. And there's some that people don't want to see happen. And I think that's also really important to understand as we're designing these technologies. We do a lot of science communication through two nonprofits that I co-run, RoboHub.org and AIHub.org. And we also went and did user studies. So we did user studies in warehouses, in firefighting, and for bridge inspection. And in the three cases, we asked them what their job was like, what the challenges were. We told them about swarm robotics, and we asked them if they thought this would be useful for them. And the promising thing was in all three cases, they said, yes, there's potential. There's areas in my work thread where I don't want to be doing this particular task, or actually no one in the company is doing this task, or we just don't have the capabilities to do this and we could use the extra help. It was also really useful to understand that there were things that they didn't want the robots to do. So for example, with the firefighting, we had created a robot that you could throw in a fire and go poof and extinguish a tiny corner of the fire. And we thought, surely the firefighters would want robots to extinguish fires. But no, that was their art of the profession. They were firefighters, and those were the areas that they cared about. And so what they wanted was robots to help them get information, not to fight the fire in a direct way. And I think it's really getting that nuance that's going to be hugely important. And finally, while they were open-minded, they all said, I'd use this technology if it was trustworthy, if it worked, if it was easy to set up. So that those things, those ifs, are also the things that we need to crack to make swarms a reality. So on the back of that, we started focusing on one area that we thought was interesting, which is intralogistics. And what we noticed is that when you think of robots in warehouses, you think of Amazon or Ocado. Those are warehouses with huge amounts of robots, actually. But those systems typically have infrastructure, and they've invested in that infrastructure and the specific robots that work for them. And this is not something that would work for a small retail shop or a pop-up warehouse or reconfigurable manufacturing location. And so there's a huge unmet need where people would use the technology if it were available and if it worked in the messy real-world environments in which they live without installing infrastructure or anything sophisticated. So profoundly, these systems need to work out of the box. And so if you think of logistics, usually you want to optimize what they call key performance indicators. You want to go fast and you want to be cheap, basically. So it's cost and speed. And I think where swarming comes in is in these swarm ideals, the zeros. Okay, so if you use adaptable, robust, self-organized systems, Can you get zero scaling effort, meaning you can add or remove robots to your problem? Can you get zero reconfiguration time? Can you get zero failure? Can you get zero infrastructure setup? Can you get zero setup time, zero training, because of the way swarms work, which you might not get with a more classical robot solution? And we hope that these zeros is actually what makes swarms usable out of the box. So I think it's sometimes hard to wrap your head around this. And so this is just a thought experiment to understand what I'm talking about. Imagine you had to set up a cloakroom at a conference if they come back into fashion. So you're at a conference and you have to set up a cloakroom, and you're the company that operates the robots for that. In a classical solution, in a centralized solution, what you would do is you would come to the environment, you would create a map of where your cloakroom needs to be. You would set up a computer, your central computer, and then the central computer would be the location where the user comes with their jacket. So they come with their jacket and they go to the central computer and they say, please pick up my jacket. And that central computer would essentially say, robot 325, follow this specific path and come and pick up this jacket. You'd put your jacket in, and then the central computer would say, okay, robot 325, or whatever number I said, go and follow this trajectory and position this jacket in this specific area, and I'm going to record that in the database. And so when you come back to get your jacket, you would essentially request your jacket, and it would look up in the database that your jacket is in this location and do the same pipeline in reverse. So that requires a map of the environment. It requires a central computer that can handle all the robots. It requires good communication. Otherwise, if the central computer can't connect, none of the robots work. And it requires your database to be precise. So if someone picked up or moved that jacket, then you'd be in a bit of a pickle. Instead, the way a distributed or a swarm system would work is that you'd arrive in the cloakroom environment, you'd put some tape on the floor, no map needed. And then you'd have the users that come anywhere around that cloakroom with a little Bluetooth app called the Cloakroom app and say, hey, I have a jacket. And then any robot nearby would come to pick up that jacket. You'd put it in that robot and scan a little code on the box. And then the robot will deposit it somewhere in the cloakroom. It doesn't matter. And then when you come back, you'll get your Bluetooth app and say, hey, I'm looking for box QR code 3. And then every robot, because there's enough of them, would look around, which is what humans do in a cloakroom, by the way. And then we'd say, oh, I found your jacket. It was right next to me, and then bring it back to you. So in that context, there's no map, there's no central control, limited communication, just these Bluetooth networks between the robots and the user. And actually, if the human wanted to pick up their jacket, that wouldn't cause a problem at all. There's no database because it's always real-time lookup of information. So this is why these systems could work out of the box. And so it's great to talk about it, but we also needed to build it. And so this is an effort with Toshiba Bristol Research Innovation Labs over the past 3 years, as well as the Umbrella Network in the South Gloucestershire region, to create what these robots in the network would look like. And so these robots are way more sophisticated than most of the robot swarms that we've designed so far. They are very fast. They're driven by drone motors, actually, even though they're ground-based robots. They've got 6 hours of battery, 4 cameras, a laser time of flight range sensor, which just gives them data to sense their environment. They've got 1 GPU and 6 CPUs, so quite a bit of computation on board. They have a lifting platform, and they can do Wi-Fi, Bluetooth, and 5G. And this is them in action. And what's interesting is here they don't have any central control. It's just them understanding their environment based on what they can perceive on board the robots. And we also have, along with that, high fidelity simulators to wrap our head around what it is these robots are doing or can do before we push them to simulation. And actually, these real robots are the same systems as the simulated, or these simulations are the same code that go on the real robots. So this also bridges us to digital twins, because a lot of what you've seen here is the robots behaving, but increasingly we're going to need a user and an operator, and these users are going to need to monitor in real time what it is the swarm is doing and be able to control and optimize the behavior of those robots. And this is really where digital twins come in, the ability to very quickly go between the virtual and the real world to wrap our head around what's happening so that we can improve it. And I just wanted to mention a couple other examples. So here what you see is another one of these real world swarms where robots are able to be used to interface with humans. So here what you're looking at is another one of our swarms. So we have 100 of these little screens on wheels, and we use them in Cabot Circus here in Bristol to ask the public how they could help act on climate change with their own personal actions. And so they could choose from a menu of different options. And what we wondered is, can these robots actually serve as physical avatars for opinions? Can they help people? First of all, give their opinion if they're a bit shy in a group setting. Well, here now you have a robot interface that allows you to give your opinion. And does it help their opinion be seen? Because now when users come in to select an option, they're able to see what other users before them have selected as well. And so that's something we've just started to explore, and we're actually looking for use case scenarios. Marahan, who's the PhD student here, is currently making these smart post-it notes. So we're trying to see if we can use these in other human social contexts to do things like brainstorming on complex topics. So I think we're at a stage now with swarm robotics where there's many areas where swarms make sense if we can just make it happen. But actually it's more than that. It's also if we can just make them trustworthy. And that's a big focus of ours with the Trustworthy Autonomous Systems program. And so here's just us scratching the surface on what we need to consider if we're going to make swarms that are safe, that people might want to use in their everyday settings. And we're doing this not just for robots. We also have another PhD student thinking about bioethics and regulation of swarms in nanomedicine. And so across these different scales, we need to think about how swarms can be used in real world contexts. So with that, thank you very much to different labs I've been in across the world before arriving in Bristol 7 years ago. And since then, we've grown a really fun team of PhD students and postdocs and collaborators, because this is all very cross-disciplinary and not possible without amazing contributions from my colleagues. So thank you very much.
Thank you so much, Sabine. That really was truly fascinating. And our alumni have also obviously found it very fascinating too. We've had plenty of questions coming in. So I'm going to move on to the Q&A now. It really touches upon what you were talking about there in terms of thinking about cloakrooms, etc. Is that impact on human jobs? And somebody's asked if there are any guesses onto the impact of robotics on human jobs in the future.
I think that's hugely important. When we did the use case studies, what was interesting is we were asking people in their profession whether they needed these robots, and many of them saw tasks that they thought the robots could be useful for. I think it's important to realize these robots don't do jobs, they typically do tasks, because they are so quite specialized in terms of what they can actually achieve. And so it's worth thinking about what tasks then can be automated or not automated, and which ones you do want automated or not. One thing that's interesting is in the pandemic, we would have needed so many types of robots, and they weren't yet there. We don't have the capabilities to do many of the things that us humans do. And I think if anything, that should have given more value to what humans do on a regular basis that we can't currently do with technology. But there is a need for these extra tasks to be done, I think, with extra helpers, which is the way I see robots. It's also worth looking at areas that have been automated for a while, like the automotive industry. And what's interesting there is that data has shown that automation in the automotive industry has increased jobs overall. But if you look locally in a community, it might have replaced or displaced jobs in that local community, because the people working in that factory, for example, might then need to go do something else. And so there, I think the question is going to be, what do you care about, the overall numbers or the local impact on individuals? And both are important. And we're going to need to figure out how to reskill those individuals so that they're able to contribute or be the users of the robots or do something that's meaningful to them that might not be exactly the same task or role that they were doing before. And that's going to be important.
Thank you, Sabine. And similarly, I suppose it's that sort of worried reaction that might happen. So we've got a question here saying, I work in an educational robotics to help teach kids to code, and he occasionally gets a worried reaction when students see the robots for the first time. How do you deal with the stigma of widespread robots?
Oh, that's interesting. We do a lot of education with them as well. So even those little coin-sized robots, we can bring them to classrooms. And I think they are a great way to get kids engaged in STEM and technology and also humanities, because I think it's really helpful to think about, well, if this robot were real, what would you do with it? I think you can think very creatively beyond STEM with these robot technologies. So I think they're a great tool for the classroom. The stigma, I haven't encountered so much the stigma with the younger generation as actually, because they come a little bit with a fresh mind and maybe are more used to encountering technology. So with these swarms, sometimes from the adults, you get questions about, ooh, a swarm that's a little bit creepy. They look like spiders or whatever. And with the kids, they're like, oh, they're just little cute little bugs. And so I think we need to tap into that kind of desire to create new and exciting things. So I haven't seen so much stigma actually from the kids. I'd love to hear more from the person who asked the question, maybe through an email about where that occurs, because maybe there's also ways of presenting the technology when it's in the classroom. So it's not just a tech, but it's a tech for good, or it's a tech for cool applications.
Well, thank you so much. And I'd encourage the person posing that question to get in touch so that we can link you up together. So a slightly different type of question here from kids to weaponization. Somebody's asked, how can we prevent the weaponization of robotics research?
Yeah, I think that's hugely important. Everything that we focus on is a civil application. So even we do some work on drones, but that has to do with how do we extinguish forest fires. And there's so many applications that require this technology because of the scale at which it can operate. But there's a clear need for potential regulation of these technologies so that they are used for the ones that people saw as a benefit to society versus the ones that they saw as a risk for society. And in that chart, the risks for society were military, actually. So I think that's something that we need to be really mindful for. There is a push in the robotics and AI community to design these technologies in the right way from the start. There's a campaign to stop killer robots in the UN, for example. And there's a number of ethics codes that are being given, not just to the researchers, but to the students as we're bringing them up to be roboticists and AI practitioners. But it's going to need more than us. It's going to need some desire to develop regulations and things from higher up. And I think that's important.
Thank you. Can you see this technology being used for outer space exploration in areas inaccessible, inhabitable to humans?
Yes, those are the funnest ones. It's places where we can't do anything else than use technology very often. So there's definitely interest in exploration using swarms of robots just because of the sheer scale that you could get in terms of coverage. If you wanted to sample, for example, in the context of astrobiology, or if you wanted to build structures. So termites are great swarms at building structures. So could you create little constructs that might be useful in space for outer space stations? The warehouses, we actually spoke to people in the space sector about warehouses and swarms, and that's also something that might be exciting. So yeah, definitely.
Amazing. Thank you so much. I can see passion and excitement coming through on these topics.
It's very fun.
It's brilliant. What applications do you see for AI-driven quantum computing and metaverse platforms in swarm robotics?
So for me, the metaverse comes through with the digital twins. I think there's a big push now that we can get these technologies into the real world to understand what they're doing and to use that from the user's perspective. So even with the swarm in the warehouse, you can imagine that interface that allows us to understand what the swarm is doing, to monitor it and control it. So imagine that you lived in a world, I don't know if this is going to be the most useful tool, but we just bought a headset to be able to do a little bit of AR with our swarm, because the swarms do stuff. They're a bit random and it's not quite clear what they're doing. But what if using an AR headset, you could probe that swarm and the swarm could tell you, hey, I'm just going to get Jack's jacket, and hey, I have no more batteries. Just something that allows you to understand by interfacing with the robot world in a more natural way. And you do need some augmented reality to do that because we're not robots. So we need a way to be able to interface. So I think that's where the metaverse comes in, is to help us interface with the technology and control it, because we'd like to be able to, just wave the swarm away and then it goes and charges itself. Where the quantum comes in is that this stuff needs more computational capabilities, because if your user says re-optimize swarm behavior, that shouldn't happen over hours. It should happen very, very quickly, so that quickly you see the effect of that. And that's where just the power of quantum computing might come in.
Thank you so much. So we've got a question here about what potential healthcare application scenarios are there? You've talked about obviously the health and treatments, but is there any scenarios where we could see that converting well into the healthcare?
Yeah, so there's most healthcare issues are issues of huge numbers of things interacting, whether they're cells or another area we've been looking at is antimicrobial resistance with bacteria. That's also collective behavior. And so how do you control those bacteria, those biofilms to treat infection? I mentioned the wound healing, the cancer treatment. I think anything that deals with collectives is really interesting. Even the immune system is also a collective swarm in my mind. So there's so much potential to understand how you control these collective systems for biomedical applications. With the larger robots, it's also worth thinking about just helpers and care settings. So for example, we were speaking to someone who manages care homes, and they already use the little robot vacuum cleaners. They're kind of used to little kind of helper robots around them. But could some of these be used to help bring some medicines or bring the food at certain times to free up time for the human caregivers to go and chat and do other things than sort of be delivering things left and right? So maybe there's some scope there as well.
Brilliant. Thank you so much. There's some questions coming through actually. That your excitement is obviously quite contagious. There are people here asking questions about getting into the sector and wanting to develop their careers there. So it says, how do you get involved in this field from a non-robotics or engineering background? So at the moment they're involved in data science, and they want how do you make that transition?
That's great. That's so the good thing is that it's so cross-disciplinary that you can come in from many different backgrounds. So in my lab, we have biologists and physicists and engineers and people who study education. So it's very, very cross-disciplinary. And we just launched an MSc in biorobotics actually this year that has this type of mix of cohorts between biologists and engineers and humanities to sort of think very holistically about how you design some of these technologies. So I wouldn't see it as a transfer, like no one trains as a swarm roboticist. We kind of just decide we want to do it and then try to find our way into it through projects or collaborations or for students through dissertations. So that's usually how people are brought into it. I think it's the open-mindedness that you don't need to come from a particular background. Data science would be hugely useful. And that's something you learn on the go anyhow. So I guess I encourage you to give it a go.
Thank you. And following on from that, actually, it said if one is interested in nanobots, is it a good starting block to work entirely in a simulated environment?
I think it's a mix. I think the simulated environment, what it's taught me is to ask the right questions. So when I was in the bioengineering lab at MIT, they were all lab people. And I did both the lab stuff to wrap my head around how it works, how you actually make nanoparticles, what it looks like under the microscope. But did a lot of simulation. And the simulation, you have to ask the question of how many cells are there and how many particles and how does it actually move through the body. And all those questions make you think about the problem really hard and figure out what's important in that problem. So I think the simulation is sometimes a great way to go to wrap your head around the problem. And then you know what questions to ask when you go to the lab to actually make the system. But probably need a bit of both, or at least to talk to the right people so that you're not just simulating for the sake of simulating.
Thank you so much. A slightly different one here. How much congruence is there between robotics research and animal behavior research?
Yeah, well, without the animal behavior research, we wouldn't have many swarm algorithms. And just as an example of that, one of my PhD students, who's now a postdoc, did his entire PhD studying fish to understand what sensors the fish use to work as schools, so to work as collectives. Because these fish could operate in really messy, dark waters, which robots can't do. And so after studying 100+ fish, he found a cool sensor mechanism, and then he 3D printed a robot sensor and then showed how it worked basically on a robot system. And so that's just a perfect example where you needed to do the animal behavior to wrap your head around what's so exciting in biology before you could transfer and abstract very often the technology to use on robots. So hugely important. There's a lot of collaborations in swarm robotics with biologists and animal behaviors. Yeah.
Great. Thank you, Sabine. Do you see any application of swarms in the development of self-driving vehicles?
Yes, because it's going to be challenging for self-driving vehicles to be centrally controlled. just because of the sheer number of robots or autonomous cars that might be on the road further down the line. So ultimately, these cars are going to react to their local environment. So if you think like something like a crossing, that's going to require a set of local rules that make those crossings smooth and roads of traffic rules. The rules that we study are profoundly decentralized, and you could probably describe them as a set of swarm algorithms. So I think a lot of the way we operate, if you can translate that, because we are also an inspiration from biology, to autonomous cars, I think a lot of those rules would be useful in the context of autonomous driving. Now, there's a lot of desire to make sure that autonomous cars, because of how safety critical they are, always work. And so I think that's where the trustworthiness comes in. And how do you verify these swarm behaviors so that if everyone follows the rules, are there no crashes at this junction? So that's going to be important.
Amazing, thank you. And we've probably just got time for this very last question. Are there any examples that you can think of where it would be beneficial for any reason where traditional robotics and swarm robotics could work together? So they were thinking about the sort of cloakroom compare and contrast, but not limited to this type of application. Do you think there would be instances if the both of them together would make it, would be a good use of their work?
That's a great idea. And as many things in the real world, the solution is a hybrid, is somewhere in between the centralized and the decentralized control. So for example, it might make sense for a large warehouse like Amazon to have their super centralized, sophisticated, optimized system, right? Because that just works in their environment. So there's no reason for them to decentralize that. But as soon as those boxes leave the warehouse, maybe to go to the truck or maybe to go to areas that are more interfaced with the messy real world, maybe that's where you transition from centralized to more swarmy type behaviors. Or actually in the swarm setting, even the cloakroom scenario, you might still want some overarching super controller, probably the human, to then be able to say, stop everyone what you're doing. And I'd like to, plan a little bit more what you're all going to do. Please all move to the left. So I think there's probably a world in which centralization to a certain extent sits on top of decentralization for different types of applications. So that's a good idea. It's a research question, actually.
Brilliant. Thank you so much, Sabine, and thank you for all those responses to the absolutely brilliant questions that the alumni audience was sending in today. It was just absolutely fascinating, and I personally learned so much today as well. So really, really thank you for your time. So yeah, just to finish off now, we'd just like to obviously extend our thanks for Professor Sabine Hauert's time and for joining us today. We really, really do appreciate your time and sharing that expertise. Thanks to you all for tuning in today. We really hope you enjoyed the session, found it interesting, informative, and also feel proud of the unique and important work that Bristol is doing in this area. Please do stay in touch. If you haven't yet joined our networking platform, Bristol Connects, please do so through our website. And we do have a busy programme of events coming up in 2022, so please do keep your eyes peeled on that for more information soon. Keep in touch, stay safe, and enjoy the rest of your day.
Bye, everyone. Thanks for the great questions.
Thank you.